Okay, I'm going to explain strategy pattern to you, but I'm not going to define it to you at first. We are going to look at a problem here, and then we are going to, step by step design its solution with given constraints and change requests and etc. And then eventually arrive at the solution. And that particular thing is going to be a strategy pattern. So we will learn it that way, and then I'm going to define it. So let's have a look at the problem. Now, what is the problem that we have? Want to create a duck simulator. So what is a duck simulator? Basically, we'll have a pond, and then we will have different sort of ducks, and the ducks can swim and ducks can make a sound, and each species is drawn differently on the screen. So okay, so we need to create a display function for each duck, and it will be different for each duck, right? So now the constraint that we have, that the catalog of duck species will grow, and product will keep sending change requests. So we are graded on the thing, how much existing code has to change each time something change or something new is added. So let's think about how we'll design the initial solution. So we have a duck, and then we have separate types of ducks. So initial solution seems to that comes to my mind is really going to be the easy one. Let's create a abstract duck class, assign it a few functions, like every duck is going to quack and every duck, as mentioned, is going to swim. And then we are going to have a display function which will be different for each kind of duck. So let's mark that function as an abstract function, right? And each duck class, suppose mallard duck class and redhead duck class, which basically extends the abstract class duck, is going to have its own implementation of the display function, right? As we can see here, a type of we have a abstract duck class, and it has a quack function, it has a swim function, and then we have marked the display function as an abstract function, right? Okay, so the quack and swim function are written once and shared everywhere, and display each class can have its own display function. Okay, now there is a change request here. So what is a change request? The manager has come to us and asking, like, competition simulator has flying ducks, our does not. So this is the requirement, we need to deliver flying ducks in 1 week. So how can we do that? A simple things that comes to my mind is, just simply add fly function in the abstract class, and that's what we will do. So we will just do that. But suppose the management came again and asked us, we want to introduce a rubber duck, and the rubber duck in the rubber duck we don't want it to fly. But since the rubber duck is going to extend the abstract class of duck, it is automatically going to have a function for fly, and it is going to be flyable. So when we open the simulator, we are going to see rubber ducks fly, which is bad. So how can we solve this problem? It is simple. We can usually, override the function fly and makes it do nothing. Something like we can do it here. Like, nobody wrote fly here, it arrived anyway, so we can just, override it. Now, that would work, right? Suppose now if we have two classes, a rubber duck and a decoy duck, and the decoy duck does not even fly and does not quacks, you know we can handle that. We can basically override fly and quack function in the decoy duck, and we can do the same. Suppose the rubber duck does not quack, it squeak, so we can override it also in the rubber duck class that we extend. Now, for the two types of species, that is not a problem. But what if we receive another change request? Like, we are adding roughly 20 new duck species now, and we have decoy duck, and decoy ducks are different types, wooden and no flight bird and no sound bird, and rubber ducks in 4 colors, and mountain ducks and sea ducks, and all separate types of ducks. Now we are going to create 20 new classes for it, and for each class we need to override 2 methods for it. So basically we are going to end up writing 40 new methods for all of them. Now that is going to be a far too much work, and the onus is going to be shifted to the developer, who is writing each class. Will need to override both of them. So that is just too much work. We are going to repeat ourselves again and again. So that is what I will call bad design. So now this is going to be a problem. How can we fix it? Maybe we can, take out the fly and quack class functions out of the duck abstract class and maybe create an interface for it. That is a good solution. So let's do that, right? Let's do that. We create two interfaces, a flyable interface and a quackable interface. Now each duck class is going to implement the interface. Suppose mallet duck implements this, and mallet duck basically also implement the quackable class, and the same for the red duck, it is also going to implement flyable, right? But the rubber duck does not implement flyable if it chooses. So it is basically, depends on the duck class, what it wants to implement and what it does not want to implement. So it works, right? And the code can look something like this. We have two interface, flyable, and one interface, quackable, and it depends on the particular duck what it wants to implement. Suppose a red duck implements both, mallet duck implements both, and if the rubber wants, it does not wants to implement both, it can, skip those, and it does not have the fly and quack functionality. And this works pretty good, right? It would work until unless we have got another change request here. And the change request is low priority, but they have asked, flight animation feels too fast. So we are required to make all the ducks fly 30% slower. Now there is a problem. We need to go and open up every class that we have wrote. Suppose there are 48 classes, we need to go over 48 files and make this one line change over and over again. So what have we done here? At first we basically put the fly function and squawk function on the abstract class, so we didn't have to repeat it. Then we had to customize the thing, so we took it out and created separate interfaces for it. Now the problem is they are getting repeated. So basically we need the best of both the worlds. We need to, put it somewhere so we don't have to repeat it again and again, and also make it configurable. So let's see and think about how we can do it. So the first principle comes here, identify the things that are varying and separate it out from the things that are staying the same. So let's think about it. What are the things that are stable right now? The swimming is stable, the display is stable, the name is stable, suppose. And what are the things that are volatile? Fly is volatile and quack is volatile. What if we can create a separate flyable behavior and quackable behavior and make it customizable for each class? Some way we can define the behavior and we can reuse it. So let's see how we can do that. Let's create a fly behavior interface, right? And let's create different concrete classes for that from that interface. Suppose fly with wings, which have a separate fly function flap, and fly no way, which does nothing, and fly with a rocket powered fuel or engine or whatever, so which has a fly function that is boost. And we create this concrete classes for a different fly behavior from a fly behavior interface. And we do a similar thing for a quack behavior, right? uh, we define the quack behavior interface which has a quack function, and then we create concrete classes from it, like quack or squeak or mute quack for the decoy duck or some kind of duck that does not quack. And let's look at the code of it, how it will look like in TypeScript. Suppose we have two interfaces, fly behavior and quack behavior, and then the fly with wings implements fly behavior, and no flyway implements fly behavior, and the quack implements quack behavior, etc. So all these concrete classes are basically going to implement the fly behavior and quack behavior interface, right? So that's where the second principle comes in. Always program to an interface phase and not an implementation. But why are we programming it to an interface? We are going to come to that, hold to that thought. But now how are we going to use it? Now that's the actual thing. Let's look at here how we are going to use it. So suppose we have an abstract duck class. What if we can add two properties in it, the fly behavior and quack behavior, and make that properties customizable, right? Using some sort of functions and assign them. So whenever fly function, perform fly, is called in the abstract duck class, is basically assign that to the fly behavior's fly function, and whenever perform quack is called, it can assign it to the quack behavior quack function. Now this is for exactly this reason we need to program to an interface, because when we program to an interface, basically the fly behavior knows, right, this thing knows that everything that is going to be, every different fly behaviors that are going to be assigned to it are going to have a fly function. So, and the quack behavior knows similarly, like every different types of quack behavior that are going to be assigned to it are going to have a quack function, right? So it needs to make that sure. That's why we basically use this. So, and this pattern is called composition. The duck class is basically composing composing of fly behavior and a quack behavior. We are assigning it two separate properties and marking it as that these two properties belong to these two interfaces, right? And suppose now we create extend it as a mallard duck and a rubber duck, which have its own display, and then we can do it. So let's look at the code, how it will look like. So here is our abstract duck class. Now it has two separate properties, fly behavior and a quack behavior, and both are defined as an interface, fly behavior and quack behavior. Now basically we can set it like this. You can perform fly, which is basically uh, delegating the fly to the whatever fly behavior is set, and perform quack, which is delegating the quacking to whatever the quack behavior is set, and we can also set it using the function, right? So suppose a mallard duck wants to call the function fly with wings, so it will create a new it will instantiate a new class and then assign it to the fly behavior in its constructor. And suppose it wants to assign a quack behavior, so it will call the new quack class and assign it to the quack behavior. Now the fly with wings class already is extending fly behavior interface, and the quack class is extending quack behavior interface, like we saw earlier here, right? So that's how it knows that, you know, this particular behavior will definitely going to have this fly function, and this particular behavior is definitely going to have a quack function, right? So basically using this way we can make the behavior interchangeable while putting the logic of it in one place. So suppose fly with wings, we want to change it, we can basically go and change it to at one place, and all the separate species of duck which are going to use this fly with wings are going to, you know, get changed, and automatically we won't have to go at each class and change it, right? We can change it centrally. Now suppose a change request come, you know, in mid flight we want to make it switchable, like the game is running and we want to give it based on a button click or something. We want to give each bird each duck rocket rocket fuel flying capability mid flight. So how can we assign that? Suppose, you know, if you want to add a custom functionality mid flight, or, you know, based on some sort of logic. Now we could not have done it if not for this composition. Adding this behavior classes and all things, what it helps us do is something like this. We create a, suppose we have a create a fly rocket powered class which implements fly behavior, and it boosts the flying, and, you know, by 30%, 40%, or whatever the logic that we have. Now in the class what we can do is suppose we are assigning it mallard duck fly, perform simple fly operation, and then suppose if we wanted to perform, you know, based on rocket based flying, then we can rocket powered flying, then we can basically just call the function, you know, set fly behavior to rocket powered flying, and then it will fly in that way. So all of that is possible, all of this sort of change request is possible because now we have following this interchangeable pattern. This is called strategy pattern, you know. So this is a little bit complicated. Basically it is following the mechanism of composition rather than just simply inheritance, right? We are composing the abstract duck class with separate fly behavior and behavior interfaces. let's look at it more, look at the pattern. So in the strategy pattern, basically it defines a family of algorithms and encapsulate each one and makes them interchangeable. Strategy lets the algorithm vary independently from the client that use it, right? So now the person or the client who creates this new class can basically, uh, a new class of duck can basically do what? It can create a separate, it can assign it different types of capabilities, or different type of quacking, or different type of flying, mid-flight, or based on some logic, without going into it or changing anything. You don't need to change any code, right? So basically we will just extend it without opening it. So let's see what are the participants here are. The context is basically duck, and we have two strategies here, the fly behavior and quack behavior. Suppose now if you want to add swim, and swim is going to vary for each duck, you can create a capability separate for swim also, right? Swim behavior, and then create concrete classes for that particular behavior. And similarly for fly behavior and quack behavior, we have concrete classes like fly with wings, fly no wave, fly rocket powered, quack, squeak, mute quack. And yeah, that's it, I guess. Right. So basically we learned three principles here. uh, Identify what varies and separate it from what stays the same, and then program to an interface and not to an implementation, because programming to an interface is exactly what lets us do the composition and favor composition over inheritances, all of which is covered. So so this is basically the strategy pattern for you. Thanks for watching this video, and see you in the next one.